Okay, all right, let's start. So last lecture we were looking at this circuit, common emitter amplifier circuit. All right, so this was the circuit, and we saw that the open circuit voltage gain AV0 was minus GMRC. Input resistance Rn was approximately equal to R pi, and output resistance equal to RC here. And we saw that the properties of the amplifier, especially these two, are influenced by ICQ, or the bias point. Are influenced by bias point, and therefore the stability is important. Stability of bias point is important, because if the bias point changes, almost everything in the amplifier changes. Stability is important. So the issue was, what can cause a change in ICQ? What can cause ICQ to deviate from the value that you want it to be? And we said there are several things. For example, these resistors that you see here, RB, RC, they have tolerances. They're not, especially when you're making lots of amplifiers, many amplifiers. In one case you may get a resistor of 1K, in another 0.9K, in another 1.1K. So these values, there's a tolerance associated with it, these resistors, tolerance associated with it, which will cause bias point to differ from one amplifier to the next. So resistors are there. The temperature, of course, was there. Temperature causes resistors to change its value. Temperature causes changes in beta. Temperature causes changes in the base emitter voltage here, the base emitter voltage that you see here. In this case, we know that ICQ is basically equal to VCC minus VBE by RB multiplied by beta. So any changes in base emitter voltage, temperature causes base emitter voltage to decrease, and so that will cause a change in the bias point. But one of the most important ones that we discussed, and supply voltage, for example, any change in supply voltage will cause bias point to deviate. But one of the most important points that we were discussing was beta. When we go from one transistor to the next, the beta varies a lot, and this is a problem that we need to address. The others, tolerance, for example, could be, say, 5%, right? Tolerance could be 5%. Change in supply voltage, delta VCC, could be also 5%. But the change in beta could be huge. Beta, we said beta could change from maybe 100 to 200. So we are talking about change in beta which is almost 100%. So beta changes a lot more. So one of the first problems that we need to solve is make our circuit insensitive to beta, right? So we want a circuit. So our goal is, we want a biasing. We want a biasing that is insensitive to beta. That's what we are looking for. This is our objective. Biasing is insensitive to beta. Now, how do we measure the sensitivity of biasing? Well, one of the ways of doing that we do here is by defining a parameter called S, sensitivity to beta, S beta, which is nothing but change in current, IC by IC, percentage change in current, divided by percentage change in beta. Percentage change in current divided by percentage change in beta. and it's easy for you to see that the sensitivity is 1 here, or 100%. You can easily take this expression, delta IC by IC, you can derive and show that the sensitivity is 100%. Okay, so it's a very sensitive circuit to any variations in beta. So we want a circuit which is better than this. All right. Okay. Now, the problem with this is, with this particular circuit, so let me redraw this circuit for you. The problem with this circuit, let me just draw here RC and RB. What this circuit is doing, right? So we said S beta is equal to 100%. What this circuit is doing is that is using these resistors RB and VCC to fix. So the strategy in this circuit, if you look at it, the strategy in this circuit is fix IB. That's what this circuit is doing. What does it do? Fix IB. How does it fix IB? Well, it says VCC minus VBE by RB. So its strategy is fix IB, the way it biases it, fix IB, and then it says IC is equal to beta IB. Then it says IC is equal to beta IB. That's how it fixes IC. So note that IB is pretty stable, right? IB will not vary with beta. IB is not going to change with beta because RB is fixed, VCC is fixed, and VB doesn't change much. So IB is fixed. IB doesn't change with beta. But IC is directly proportional to beta. So IC will change, 100% variation in this thing here. So the strategy is wrong. The strategy of biasing is wrong because you're fixing IB, and so you're making IB very stable. You're making IB stable, but then IC is simply beta times IB, so IC is very unstable, with variations in beta. So what should be the new strategy in the new circuit? Obviously, I should concentrate on IC, right? I have to make IC stable. Okay. So in the new strategy, suppose I draw a new circuit. A new circuit as an example. Look at the strategy here for a moment. So let's add the signal we are putting here. Okay. Signal we are putting here. All right. So in the new strategy, suppose I do this. I add a minus VEE here, and there is a VCC here, there is an RC here, and I put a signal here directly. Okay, and I will put a capacitor here. Bypass we will do. We'll put a bypass because we don't really need this one here. Suppose I do this. What is the strategy here? What are we doing here? Now note, in this case, if you were to do the biasing part, for biasing, what will you do to the signal? If I were to look at the biasing of this particular circuit, what happens to the signal? Signal will become ground. For biasing, you will put it to ground. For bias analysis, you'll put it to ground, right? And capacitor you will open. All right, capacitor you'll open, so you'll get this. Now, what do we get? This is 0. This voltage will be minus 0.7 approximately. And this is VE. So what do you get? A current which is nothing but IE. So the strategy here is the following. Fix, note that is very different. Fix IE. Fix IE. And IE equal to what? Minus 0.7 minus this, so plus VE by RE. By RE. So it's fixing IE. In the other case, it was fixing IB. through the supply voltage and resistor. Now it says we know what is the relationship between IC. IC is nothing but beta by beta plus 1 IE. Two different approaches to biasing. In one case, it says fix the value of IB through this supply voltage and through these resistors, and then derive IC from IB by multiplying it with beta. In the next case, it says fix IE, right? So look at these two expressions here, these two here, this one and this one. This one and this one, right? Now note that IB is stable. IB is stable. IB is not varying. IB is stable. In this case, IE is stable. There's no beta here. First order, there's no beta. Okay? IE is stable. So let's look at the stability of IC. Here, for example, if beta, let's say beta goes from 100 to 200. Beta changes from 100 to 200. IC will then go from, let's say, 1 milliampere to 2 milliamperes. Look at the variation. Beta doubles, IC doubles, right? In this case, for example, if beta goes from 100 to 200, what do you think will be the variation in IC? IC, let's say we have fixed the value of IE to be 1 milliampere. Okay, let's say we fix the value 1 milliampere. IC will be, for 100, if my calculation is correct, it will go from 0.99, and if on the other hand is 200, it will go to 0.995. That's all is the change that you will get. Milliamperes. What is the percentage change? Delta IC by IC is how much here? 0.5%. Delta IC by IC here, as we said, is 100%. Look at the two strategies. Let's divide it into two. In one case, IB is being fixed by the supply voltage and resistor, and IC is being derived from IB. And in this case, the IC is very sensitive. In the next case, IE is being fixed through the resistor and supply voltage, and IC is being derived from IE, and it is very stable. Same transistor in both the cases. Same variation in beta, 100 to 200. In one case, IC hardly varies. 0.99 to 0.995 hardly varies. In the other case, IC varies so much. So if you look at this biasing, in the first case, IB is pretty stable, right? IB is pretty stable. IC varies a lot, and therefore IE will also vary a lot. In the next case, what do we have? IE is stable, IC is also stable. What will vary? IB will vary a lot. See, if beta changes, if beta goes from 100 to 200, something has to change. So in this case, what they've done is they said, okay, I'll make it stable. Now, if IC is stable, obviously IB will change a lot. Okay, IB will change a lot, and what will be the consequence of change in IB? See, both are, I mean, in some sense, this thing, if you go back and look at it, the AV0, if you look at AV0, is minus ICQ RC by VT. So for gain point of view, you require very stable ICQ. But R pi, on the other hand, R pi equal to Vt by Ib. So from, if you want input resistance to be fairly stable, this thing, then you want Ib to be stable. You can't have both in these cases. So you can make IC stable against variations in beta. So fine, ICQ is fairly stable, but then the IB will vary here. Okay. So in most of these cases, we are focusing on the IC part here. We are looking for making IC insensitive to beta, and therefore this is not a good strategy here. There's not a good strategy here of biasing. This is a better strategy because IC does not vary. But there is a problem with this, and the problem is that here we use a single supply, here we are using a dual supply. We have to use a 5 volt here and a minus 5 volt here, dual supply here, right? A dual supply voltage, plus 5, minus 5. So that makes the circuit a little bit more complex. Okay. So the next thing is, can we make the circuit single supply? So let me go back and write this circuit here. So look at this biasing here. So we said this biasing is reasonable. I'm only showing the biasing part here. VCC, RC, and RE, and minus VE. So we said this biasing is nice. It makes IC beta insensitive, but it uses the negative supply voltage here. So can I now get rid of this negative supply voltage? And still, so the idea is that I would like to fix IE. I would like to fix IE. And from IE, then derive IC. IC is equal to beta by beta plus 1. So that's the key idea in this particular circuit here, right? IC is being derived from IE. So it says fix IE. One way of fixing IE was, well, this is 0, this is minus 0.7, this is minus 0.7. That's how we're fixing. This voltage is minus 0.7, this is minus VEE, and you fix IE. That's one way of doing it. But there are other ways of doing it also, right? So what is required to fix IE? What is required to fix IE? That the voltage drop across this particular resistor needs to be defined, right? A fixed drop across the resistor, and that divided by RE gives the. So effectively, what we are saying is, how is it fixing IE? IE equal to the net drop, VE, the net drop, the net drop across the resistor RE. So let's say, basically the net drop VRE, the net drop across the resistor RE divided by RE. So we need to somehow fix this. We need to fix this value here across this resistor here. Divided by RE gives us the current, but without using negative supply voltage. Okay, without using the negative supply voltage. So if I don't want to use the negative supply voltage, let me draw now the circuit here. So I would like still the same circuit here. I would like to fix here, but I don't want to use negative supply voltage, so I'm going to put ground. I'm going to put ground. RC is going to be there as usual, right? Now I want to fix this voltage here. I want to create a voltage at this point. I want to create a voltage at this point such that this minus 0 will give me VE, a drop across this divided by RE will fix the value of IE. So how do I create a voltage at this particular point? Well, what I do is, the strategy is, I need a voltage here, right? As an example, suppose this RE is equal to 1K. Just as an example, say this RE is equal to 1K. And I want a current of 1 milliampere. How much voltage am I looking for here? 1 volt, right? If I'm looking for 1 volt here, how much voltage should be at this point? 1.7. So the idea is that to get a 1 volt here, I need 1.7 here. So now if this is, let's say 5 volt, what I do is I create a voltage divider. I create a voltage divider here. The idea of this voltage divider R1 and R2 is to create 1.7 volt here. Right? That's the purpose here. So create a voltage divider to create 1.7 here. This 1.7 will create a 1 volt here and will give me the value of the emitter current here. Right? So that's how we arrive at this particular biasing, R1 and R2. The whole idea behind this is to create a suitable voltage here. If you wanted 2 volt, then you have to create 2.7 here. Okay, so that's how we arrive at this this kind of a voltage divider kind of a biasing here. But there is one problem that you notice here is, the problem that you notice here is that it's not a pure voltage divider. It's not a pure voltage divider, because the current that's flowing here, in a pure voltage divider, the current that flows here is the current that flows here. But here now what? There is a current that flows here. There's a current that flows here. And this current is what? IB. And note, what did we say? IE is stable. IC is stable. Stable means constant value. But IB would be variable. Now, so IB would be variable here. Now, if IB is variable, it will cause this voltage to change. It will cause this voltage to change. And if this voltage changes, then this voltage changes, then again my IE and IC will become beta dependent. So now what I have to do is I have to make sure that this IB which is flowing doesn't change this voltage. How do I do that? Well, let's say this current I1 is there. What we need to do is that make this current I1 much larger than IB. Right? This current I1 that flows here, if you make it much larger than IB, then this current is I1, the same current, almost this current I2 is almost equal to I1, and it acts like almost like a pure voltage divider. So this condition must be there. You have to make this current, you have to bias it in such a way that this current flowing in this particular branch is much larger than IB. So IB, even if it changes, is not going to do anything to this voltage here. It's not going to do anything to this voltage. And so IB plays very little role. It's not going to do anything to this. And so this point is going to be stable. This point is going to be stable. IE and IC are going to be stable. And therefore, I have achieved my objective here. Okay, so this condition, we must keep that in mind, that this current flowing in this voltage divider has to be much larger than IB. And if you ensure that, then your bias point is going to be fairly stable. Okay, so with that, we come to a new circuit for our amplifier. A new circuit for our amplifier is here. It's a single supply circuit. So we have our RC, we have our VCC, we have our RE, we have R2, and we have R1. And now, see, the whole arrangement is for biasing. R1, R2, REs are all there for biasing. And we are saying that this is a replacement for this circuit, right? The replacement for this circuit. This was the original circuit. We are saying that this would be better than, in terms of stability, this was my amplifier. Right? So we are trying to replace this by this. Now in this circuit, if we note that the gain AV is minus GMRC, the emitter is ground. So under small signal condition, to maintain emitter to be like ground, so we put a RECE, bypass capacitor here. So that when we do small signal analysis, the capacitor will act like a short. So this circuit will turn out to be like this circuit here. With emitter as ground, here also emitter will become ground under small signal analysis here, okay? So that's why we put the capacitor here. And similarly, we couple the signal through a capacitor here, so we couple it here through the signal here. We couple it here. We put here Vs. And if you want to connect the load, well, you can connect the load here. So you can connect the load here, RL. So we take the output here, right? So we arrive at this particular circuit here. A common emitter amplifier with a voltage divider bias with more stable bias point. With more stable bias point. Okay. So this is a simple amplifier that we discussed. This is a better biasing. Otherwise, this amplifier is very similar to this. Except for R1, R2, all these RE are being used for achieving a better bias point.
But sir, in both the scenario, we can't fix, we can't have a case in which AV0 and input resistance.
Yeah, that is true.
In any case.
I mean, in these kinds of things,
Will be stable and will.
That is true. But there's a difference between the two. You are right. In this case, let's say IC, IB is stable, and IC is not stable. Correct? In this case, IC is stable, but IB is going to change a lot. Right? So in this case, you're right. What will happen is AV0, which directly depends on ICQ RC by VT. So that's not stable. But R pi, which is VT by IB, may be stable, right? It's stable because IB is this one here. While in this case, AV0 is okay, and in this case, R pi is not okay. But there's a difference between AV0 and R pi. AV0 and R pi, there's a difference in the sense that gain we want 40, 50, 60 or whatever precise value. The input resistance, normally what we want is we want to make input resistance much larger than the source resistance, any source resistance that is there here. We want to make it much larger than, so that the input resistance. So as long as input resistance, let's say, suppose RS is 100 ohms. RS is 100 ohms. And if you can ensure that minimum value of Rn is 1K, right? So let's say beta varies from 100 to 200. Beta varies from 100 to 200. So for beta equal to 100, suppose you can ensure Rn equal to 1K. Okay? So Rn is much larger than Rs at beta equal to 100. Okay, no problem. Rs will not have much effect on your overall amplifier. If beta goes to 200, what will happen? If beta goes to 200, instead of 1K, it will become 2K. It will become 2K. Well, it's still much larger than Rs. Doesn't matter. Doesn't matter. 2K, fine. Much larger than Rs, still no effect. On the other hand, if IC doubles here, you know, if I change beta and if IC is doubling here, well, instead of 50 gain, maybe you'll get, if IC doubles, maybe you'll get a gain of 100. But it's not as simple as that. You'll say, oh, I got even more gain. We saw that if you double the current, it may be that the transistor goes into saturation. So you have all those problems that are occurring. So this is, in some sense, AV0 is far more critical than the value of Rn. All you have to ensure is that Rn is larger than a certain value of Rs. So what you need to check is that for the minimum value of beta, you have adequate amount of input resistance. If you can ensure that, then it's okay. It doesn't matter. The actual value of Rn may not matter. While the actual value of the gain, AV0 and ICQ, they matter a lot. So that's far more critical than the actual value of IB. Okay? All right, so let's do the analysis of this one then in more detail. So let's draw this. Okay, so we have done this. All right, so let's give an example here. Okay, just the biasing is being given for a moment. VCC. So let's say I choose 1K. Let's choose 5 volt. Let me choose 1K here. Sorry. 1K here. And what I'm asking you to do is the following: R1 and R2. I want a current of IC of 1 milliamperes. 1 milliamperes, right? Find suitable value of R1, R2 to give me 1 milliamperes here. Okay, this problem all of you do on a separate sheet and sum it. I want the value of R1 and R2 such that I get a value of IC equal to 1 milliamperes. I've given the value of RE. Beta 100. Let's use beta, nominal value of beta. Beta, of course, we know now it changes, but nominal value of beta is 100. What is a suitable value of R1 and R2? So the strategy, the way, let me tell you, what would our strategy be? See, if IC is equal to 1 milliamperes, how much is IE? I is also 1. So what is the value of this voltage? 1 volt. So value of this voltage? 1.7. All right. So this much we know. This R1 and R2, we want it to act like a voltage divider, right? So which means VCC R2 by R1 plus R2. We want it to equal to 1.7 volt. But that's not going to give us R1 and R2. That's not going to give us R1 and R2. What else do we want? What is the other condition that we should try and satisfy? That I1 or this current here, right? This whole current here. This whole current here, I1 should be equal to basically I2. So this whole current here, which is VCC by R1 plus R2, it should be what? This whole current should be, this current flowing in this branch should be much larger than IB, right? So IC by beta. So IC by beta is 10 microamperes. 10 microamperes, right? So that is going to give you, VCC should be much larger than this. Now it's a question of how stable do you want? Much larger. Maybe you can take a factor of, let's say 10 or at least 10. Minimum factor that you should take is factor of 10. You could take 20, you could make it better. That's okay. So at least if you take a factor of 10, then what we are saying is VCC by R1 plus R2 should be much greater than 100 microamperes here. Okay. Now with this constraint and this constraint, you should be able to get what is the value of R1 and what is the value of R2. Should be able to find the values here. This is our IB. R2 of 17 kilo ohm. R1 is how much? 33. Okay, so check that. R1 is 33K and this is 17 kilo ohm. If we assume this factor of 10, we assume this particular factor of 10. Okay. Okay, so for this circuit then, so we put here 33K and we put here 17K, right? 17K. So let's now do a complete amplifier analysis for this circuit. What I want you all to do the following. Let's draw this 1K and 17K, 33K. Now let's add a capacitor here. Let's put here 1 microfarad capacitor here. Let's put here also, let's put here also 1 microfarad capacitor here. VCC was 5 volt and 1 volt here. 2 volt here, and let's put this 2K here. All right, V0 by Vs. So the first thing is, we saw in an amplifier like this, we have seen earlier, would have a characteristic like this. If we were to plot the gain, the magnitude of the gain versus frequency, it would look like this. It would look like this. This is our midband, where things are midband frequency range. So in the midband frequency range, the first thing that we would like to do is, in this midband frequency range, we would like to calculate the gain AV0, V0 by Vs. We would like to calculate Rn. We would like to calculate R0. These are the first things that we need to calculate. Bias point we've already calculated. Bias point, we said ICQ is 1 milliampere here. And VCEQ, quiescent point or bias point, 1 milliamperes, 2 volt drop here, 1 volt drop here, so this is equal to 2 volt. So bias point is already done. We want to find out the gain, input resistance, output resistance. These are straightforward, simple numbers. Yeah, you can write AV0, Vin, V0, Rn, R0. These are straightforward. Minus GMRC. Find out how much it is. R pi, how much it is. RC, how much it is. Write down these values. These are typical numbers, typical values for your amplifier. So these are, I think, if you calculate gain of how much gain? 38. Gain of, I think, minus 76. And R pi of 2.6K. kilo, RC of input resistance of 2 kilo. Right? These values, okay? 76 is okay, 2.6K and 2 kilo. Another thing that all of you are in a position to find out also is this value here, 3 dB frequency, FL. We looked at how to find FL. Let's call this capacitor CB and let's call this capacitor CE. So the way to do FL is to calculate FL, draw the complete small signal equivalent circuit of this amplifier. Small signal equivalent circuit of this amplifier. Okay? Small signal equivalent circuit. And all you have to do is recollect some of the things that we did earlier. All right, so the way, let me draw the circuit here in small. This is our amplifier. Right, small signal equivalent circuit. The way we draw. Well, the resistors, note that. So let's start here. Let's draw the small signal equivalent circuit here. Let's draw the supply. This is our VS. Let's draw the capacitor, this capacitor here, CB, which is, we are given 1 microfarad, 1 microfarad. Note that the two resistors R1 and R2, when you do small signal, this point will become ground, the resistors will become in parallel. This will become R1 parallel R2 at this point. Now comes the transistor. The transistor we are going to replace by its hybrid pi model here. So we'll replace, we are doing a low frequency analysis. We'll replace it by R pi. We'll replace it by GMV pi. R0 we are going to neglect. So that's my transistor, base, collector, emitter, and then back to the rest of the circuit. We have to put here RE, put here the capacitor here, CE, and put here at the collector node, put the resistor RC and ground, and this is a V0. Right, this is the complete small signal equivalent circuit of the amplifier. Okay, the values we know. R1 was 33, R2 was 17, RC was 2K, RE was 1K, R pi we know 2.6K. So all these values we have already calculated. So we know all these. R1 parallel R2, you can calculate how much is that. Okay, this is fine. Do you recall the lower cutoff frequency? What was the strategy? There are two capacitors. If there was only one capacitor, lower cutoff frequency is going to be what? F is going to be 1 over 2 pi a capacitor C times the R effective resistance seen by the capacitor here. So our assumption is that what you make an assumption is you'll say, well, maybe this is what is causing the lower cutoff frequency. And the other capacitor you assume to be short. The other capacitor you assume to be short. So why don't you do one thing? Say this is causing the lower cutoff frequency and you assume CE to be short. So what is, we call this FB because it is there. So FB is going to be 1 over 2 pi CB. And what is the effective resistance seen by CB? With CE considered as short. Effective resistance seen by CB is what? Note that CE is short. So effective resistance seen by CB? R pi parallel R1 parallel R2. That's it, because this point emitter is short, right? So that's it. R1 parallel R2 parallel R pi. Calculate this value. How much is this coming out? 2.1K. Okay. 2.1K. Really? CB is 1 microfarad. Oh, 2.1K is this resistance, okay? So multiply it by CB, which is 1 microfarad, and calculate. CB is 1 microfarad, so what is the frequency? So I think R1 parallel R2 is around 11.22. Yeah. How much is this? 2.11K, so how much did you say? 75? All right, around, I think that's what I'm getting, 75 or so, 75 hertz. Maybe similar, okay, 75 hertz. Let's say what some slight deviations may be here. 75 hertz. 75 hertz. So that's due to FB. If FB was the capacitor, if CB was the capacitor causing 3 dB frequency, the 3 dB frequency would have been 75 hertz. Now let's test our other assumption. Other assumption is, well, CE is causing the 3 dB frequency, and CB we will consider as short. So if we do that, then this will turn out to be F equal to, again, 1 over 2 pi CE. Now effective resistance seen here. What is the effective resistance seen here? Remember we said when you look from here, what is the resistance that you see? We've done that previously.
RE parallel R GM
RE parallel. See R1, this resistor here will come in parallel. This will get shorted. So this will not come. So it will basically be R pi by beta. So everything gets divided by beta. So R pi by beta. This is the effective resistance that comes in here, which is the resistance seen by CE. So how much is this value? RE parallel R pi by beta. R pi by beta is very small. R pi by beta is only 26 ohms. And this is 1K. RE is 1K. So this number turns out to be how many hertz? How much is it? Is it 6.3K? .3. Okay. All right. So then FB is 75 hertz and FE is 6.3 kilohertz. So what is going to decide my lower cutoff frequency is this higher value, 6.3 kilohertz. So what we get is FL is equal to 6.3 kilohertz. Lower cutoff frequency. So we found out gain, input resistance, output resistance, and we've also found out FL equal to 6.3 kilohertz. Okay. Now, what is remaining now for this amplifier? Well, you may want to find out this also, because now what you are saying is my amplifier is going to work between these two limits, FL and FH. So you may want to find out what is FH here. What is the upper cutoff frequency? All right, so let's see how we can do that. So in upper cutoff frequency, what we need to do is, this is the small signal equivalent circuit which we built was for low frequency. Low frequency. The mid frequency, we would have shorted this, we would have shorted that, you would have obtained mid frequency. Now what we need to do is obtain the small signal equivalent circuit, small signal equivalent circuit at high frequencies. At high frequencies, okay? So that's what we need to do. So again, we need to take our amplifier like this here and build a small signal equivalent circuit. So let me do that for you. Again, our amplifier, just keep that in mind. Amplifier is here. right? Amplifier is here. So let's build our circuit. All right, so let's start with this source here. So we have a source. We have a source. The capacitor now, because we are doing high frequency, the capacitor we will consider as short. As usual, we have this R1, R2. R1, R2 will become in parallel, so we'll put here R1 parallel R2. Now comes the transistor. Now transistor model, high frequency. So in transistor model, we said when you go to high frequency, include this resistor, the transistor resistor, which was RBB, extra resistor here. Put here R pi. Include a resistance, capacitance C pi. This is my emitter node. As usual, there's going to be this current source here, GMV pi. And then this is my here. And in between, include this capacitance here, C mu. C mu. And then the rest is the usual circuit here. Here is where we have connected RC. And because the emitter capacitance is a short, so this is ground. This becomes my high frequency equivalent circuit. So values that we know are R1 parallel R2, we know from previous one was R1 parallel R2 was 11.22. So we know this 11.22K. We know this is 2.6K. We know, of course, this is 2K. Now in addition, we know GM is 0.038 mhos. What we need is the value of C mu, we need the value of C pi, and we need the value of RBB. Okay? And we have seen in bipolar transistor model how to estimate these things, but let's, for the time being, let me give it some value here. Let's say this is 1 PF. These are small values. C pi is, let's say, 100 PF, and RBB is, let's say, 100 ohms. Okay, some arbitrary values I've given it here. So here, one way of doing this is that, upper cutoff frequency is done as FH equal to 1 over 2 pi. What people do is the following. They take this capacitor C pi, find out what is the effective resistance seen by C pi. We call it R pi. Note that this is capital R, capital pi. Effective resistance seen by C pi. Similarly, what you do is find out C mu, what is the effective resistance seen by C mu. Sum up all the time constants. This is called the open circuit time constant approach. Open circuit time constant. I mean, the idea is very simple. The idea is, well, assume that C mu is not there, open circuit it, calculate the time constant due to C pi. Assume that C pi is not there, calculate the time constant due to C mu, and then do it. And then put an approximate sign here, FH. The other way of, so one can do that. We know how to calculate the effective resistance R pi, effective resistance R mu given in a circuit. We saw how to calculate the effective resistance between any 2 points. Okay. The other way of doing this is, which gives you more insight, is the following. This is based on the following. Let's say you have an amplifier you have Vi, V input and V0. There's a theorem called Miller's theorem. Okay, Miller's theorem. Let's try and understand this Miller's theorem here. What it says is the following. Let's say there's a capacitor that is connected here, C. So this is our amplifier, okay? This is our amplifier. There's a capacitance connected between input and output. Now Miller's theorem, and let's say the gain of this amplifier is A. Okay? Miller's theorem is saying the following. Miller's theorem is saying, well, this circuit, you can convert it into this circuit. You can convert it into the following circuit. This capacitor C, take it out from the feedback loop, and you can convert the capacitor into two capacitors, one capacitor at the input and the other capacitor at the output. The capacitor which was connected between these two ports, you can take it out and put it here into two capacitors. This capacitor, let's say this capacitor, let's call it CM1, Miller's capacitance 1, Miller's capacitance 2. CM1 approximately equal to, let's say, C1 minus, this is the voltage gain, AV, 1 minus AV. And CM2 equal to C1 minus 1 over AV. Okay, it says that you can take this capacitor out and you can break it into two capacitors, one capacitor at the input, CM1, C1 minus AV, the other capacitor at the output, C1 minus 1 over AV. Okay, now this is very interesting. We can go into the proof of this at a later time. This is very interesting because let's say there's a capacitor of 1 PF, right? There's a capacitor of 1 PF, and let's say there's a gain of minus 100. There's a gain of minus 100. Now, what does it appear to the input? Note that this capacitor of 1 PF to the input, what does it appear as? 101 PF. To the input port, when I look from here, this capacitor C appears as 101 PF. It is a very large capacitor getting multiplied by the gain. To the output, what does it appear? To the output, it appears as almost as 1 PF because gain is large, AV is like 100, it's almost like 1 PF. This is very interesting. You can take the capacitor between input and output, take it out, and put two capacitors, one at the input and one at the output. The one at the input is getting multiplied by the gain. This is what is called as Miller's effect. This multiplication. There are capacitors which is connected between input and output. To the input, it appears, this capacitor appears as a large capacitor which is equal to original capacitor multiplied by the gain. That's why these capacitors which are there in the feedback loop, in the feedback part, even though they are very small, they can get magnified when you look at the input side. Okay, now how is this Miller's theorem relevant for us? Well, if you go back here and look at this, this is our input and sort of output port here. This C mu that you see here. Now this is what we can call this voltage here. Let's say the voltage here is V in and the voltage here is V0. The voltage here is between here and here is V pi or whatever, right? So this capacitor C mu So what is the gain between this point and this point? Is the voltage gain, right? This resistor RBB is small. Okay, so there's, it's basically V0 by Vs is nothing but V0 by Vin, because the drop RBB is small, 100 ohms, and this is 2.6K. So it's usually V0 by Vin is basically the gain here. So what one is saying is that this capacitor C mu you can take it out and you can substitute it by two capacitors, one at the input and the other one at the output. So you take it out. We can take this out C mu, and what you can do is you can put it as another capacitor here, which is equal to C mu 1 minus AV, the gain of the amplifier. And you could take another capacitor here and put it here, ground here, which is, if the gain is large, this is practically equal to C mu, which is practically equal to C mu. Okay? So we've taken the capacitor out and replaced it by these two capacitors here. So now what will be the 3 dB cutoff frequency? These two capacitors now will come in parallel. So we can easily now write, if you look at it, we can write FH, it becomes very simple. 1 over 2 pi. What is the net capacitor that we see here now? C pi plus C mu 1 minus AV. C pi plus C mu 1 minus AV. So that's one capacitor. What is the resistor seen by this? What's the net resistance seen by C pi combination here? This will be short. R1 parallel R2 gets short here. So you see what? Everybody sees this? Resistor seen by this is RBB parallel R pi. That's the resistor seen by this. The next one is this C mu, which sees simply C mu times RC. That becomes my 3 dB cutoff frequency. That's the second term is nothing but this part here. Effective resistance by C mu is RC, and the effective resistance seen by this combination here is R pi in parallel with RBB. R pi in parallel with RBB. If I had an RS here, then of course you would have had to take RS also into account. RS in parallel with R1 parallel R2 plus RBB in parallel with this, you would have had to do that, okay? So that's how you end up calculating the upper cutoff frequency. So I've given you the values. I've given you C pi was 100 pf, C mu was 1 pf. Why didn't you calculate an RBB? Calculate the value of FH. How much do we get here? How much is the FH? What value do we get? Did we get the value of FH or not? 1, 2, 3, 4, 5, 6 megahertz, right? 7.45. 7.45. 45 megahertz. Okay. All right. So we can go ahead, if these values are correct, we can go ahead and put here FL. We got 6.3. By considering gain equal to 100, gain is 76. Gain is not 100, gain is 76. Anyway, so you can recalculate and it will be a little bit different there. All right, so we have FL and FH, but just so that you understand this concept of Miller's effect, let me ask you to do this following problem. Say there is an amplifier like this. Okay? There's an amplifier like this. It's given that its open circuit voltage gain is minus 100. Its input resistance Rn equal to 1 kilo ohm. Its output resistance R0 is also 1 kilo ohm. Is also 1 kilo ohm. And it's also given that there is a capacitor connected between here, which is 1 pf, right? And then we add a load here, RL. We add a source here, Vs. We add here Rs. Rs of also 1K, less for simplicity. RL of also 1K. And suppose I want you to calculate what is the upper cutoff frequency FH. How would you do that? Apply Miller's theorem. FH using Miller's theorem. See whether your answer comes out to be FH approximately, first order, 1 over 2 pi 100 pf multiplied by 0.5K. See if it comes out to be that. Check it. Check this out. Approximate value. Okay, you do that later on. Do this later on as a homework problem. So let's come back now. Come back to our circuit. Do we now understand this circuit well or not? There are some things which are still missing from our analysis. But before we do that, this is the amplifier that we've been talking about, VCC, RC, RE, R1, R2, okay, this is the amplifier that we've been talking about. Now, if you understand this particular one, let me ask for changes into this thing here, okay? RE. Suppose somebody does the following to this circuit, says that this capacitor is not necessary. Short it. It's not required. Anyway, for AC you're saying it's a short. Right? Why not just short it? You're right. For AC, you're saying it should be a short. So why not just short it? Why put it? Can I do that? What would happen to biasing? Yes? What would happen to biasing?
Previously, we needed a higher voltage, let's say 1.7.
Okay.
And,
No, so in this case, what would happen? Suppose somebody did that. What do you think will happen to the amplifier? Somebody says, anyway, you're looking at this capacitor, you're saying capacitor is acting like a short. Well, let me remove it. Let me just connect it directly. Okay? What would happen to the biasing? How would you calculate the bias point? What do you do to calculate the bias point? What do you do to the source? Short, right? So you will say, well, to calculate the bias point, let's calculate the bias point. To find bias point, I will remove this here. I will say, consider this as a short. I will put this as ground, right? So now this node becomes 0. How will I get, to bias it I need 0.7. How will I get 0.7? I won't be able to get 0.7 here. Plus I need a drop here also. This becomes 0. So the transistor would be in cutoff. Cutoff state. It won't be biased at all. It won't be biased at all. 0. There's no voltage to bias the transistor. So the capacitor is needed. Without the capacitor, that node will end up being 0 volt. Okay, so the capacitor is required. Okay, so if we realize that this capacitor is required, all right, so let's go back. So we know that this is essential. This capacitor is essential. Well, somebody may say, well, okay, this capacitor also, sorry, this we were saying was CE. Somebody may say, well, this also you were considering short. So why not remove it? Why not remove it? Why have this capacitor also? Now what will happen? We remove the capacitor. Right? We remove the capacitor. Now remember what this value was for us? 2K, 1K, this was 33K, this was 17K. If somebody suggests, well, I don't need a capacitor here, right? We can do a DC is no problem. DC is still R1, R2, RC, RE. Bias point is okay, no problem. What about small signal analysis? What do you think is the gain now? AV0 now. Earlier it was AV0 was minus GMRC. Now what is the changed value here?
Minus GMRC by 1 plus GMRE.
Yes, but everybody please make sure that you know this, that this is something again we did right in the beginning, that this, what would happen is this will become minus GMRC by 1 plus GMRE. Now if you recall, GMRC for us was how much? The value of GMRC was 70.
Minus 76.
This was minus 76. GMRE is going to be about 38. 38 plus 1, 39. So 76 by 39, this number is going to come out to be approximately 2. Yeah, RC by RE. So instead of a gain of 76, you're going to get a gain of 2 if you don't keep C. if you don't keep the capacitor. So this bypass capacitor that you see here is necessary, CE. What it does is it makes, for small signal, it makes this as a small signal ground. If this is not there, then this factor will come in the denominator, 1 plus GMRE, and the gain collapses. Instead of getting a gain of 76, you end up getting a gain of 2. The whole gain collapses. So that capacitor is also essential. You can't take it off. Unless you're looking for a very low gain, 2 or 3 or 4, then it's okay. Maybe you want to keep it. So this capacitor is also required. This is also required. This is also required. We can't touch this. We understand why it is there. Okay? All right? Okay, so both are essential. Fine. Let's get rid of this. Both are required. So, all right. Well, somebody may say, okay, this is where we connect the load, so let me leave it. Somebody may say, well, what if the person does this? Somebody draws a circuit like this. Says, why do all this? Just do the following. What is the problem with this? With this circuit?
IC is not fixed.
Huh?
IC is not fixed.
It defeats the whole purpose of biasing, right? The whole purpose of biasing was to generate a voltage here and then across RE, so it destroys the whole biasing. But otherwise also, what will it do? Do you see that it's a problematic circuit? I mean, this voltage divider was trying to do what? Generate 1.7. How can you apply 1.7 across the diode here? So you're heavily forward biasing the diode. So the circuit is not properly biased. If you just simply remove RE, the circuit is not properly biased here. You have to keep RE. You have to keep RE. RE is the one which is deciding the current. So RE is required. What if somebody says the following? Oh, well, why keep R2? Don't keep R2, keep R1 only. What is the problem with this? Remember what the goal is in all this? You want to generate a value here. Current IE is equal to VE by RE. Right? VE by RE. And VE, you should make VE what? Independent of base current. VE should be independent of base current. Now VE is whatever this value is minus 0.7 times this. Who decides this voltage now? This voltage is what? VCC minus what? VCC minus IB times R1. That voltage becomes function of IB. We don't want that. We don't want IB to appear anywhere because IB is going to vary a lot. So my whole voltage becomes a function of, this voltage becomes a function of IB. That defeats the purpose. We want to generate a value of IE which is independent of beta. It defeats the purpose here. That's why this resistor R2 is there. This R2 is there so that this current is much larger than IB. This whole current is much larger than IB. That's the purpose here. You want to provide a path for this current to flow back to ground here. Right? You want to do that. Otherwise, so you're seeing that all the resistors, R1, R2, RE, capacitors, you're saying each one is essential. You can't just take something out and hope that the circuit would work properly here. Okay? Now, before we leave this particular topic here, I want to address the one last maybe issue associated with that. Let's draw this circuit again. R1, R2, RC, RE, here, and here our amplifier, Vs. And let's take the values that we took here. RC was 2K, RE, just for discussion's sake, 1K, this was 17K, 33K, and remember the biasing was ICQ was 1 milliampere. For that, this value VC, E, Q, there's going to be 2 volt drop here, 1 volt drop here, and 3 volt, right? This VCEQ will be equal to 3 volts. So that's the biasing. So one last thing that we want to look at is I want you to pay attention to this value voltage here at this node here, VC. This VC, the node collector voltage. And what I want you to note is that at this point, the net voltage at this node, VC, is going to be the DC value, VC, plus a small signal value, VC, small here. Right? This voltage here is going to get amplified and appear over here. So it's going to be this. Right? And I want you to draw the following. Look at this plot here. We want to draw VC as a function of time. So what is the DC value here? DC value is 5 minus 2, 3 volt. Okay. Oh, by the way, this is 3 and this is 1. So VCEQ is 2 volt here. This was not 3, which was 2 volt here. Okay. So the DC value, the first value is let me draw by dotted line, 3 volt. Okay. This is my DC value here. Let me also draw, just for the sake of, what is the value of the voltage here at this point. The value of the voltage at this point will be what? 1 volt drop. Let me draw here, 1. Correct? This is what my emitter voltage. And note that the emitter voltage, every voltage has a DC component and an AC component. But at the emitter voltage, what is the AC component? Because of the capacitor, it's a short. So the net voltage here is going to remain 1 volt. This is emitter voltage here. Okay? The collector voltage is made up of DC plus a sinusoidal part here. So let me draw the sinusoidal part here. Sinusoidal part would be, will go like this. Right? Will go like this here. What is the magnitude of the sinusoidal part here? How do we calculate this? Let's call this as V0M maximum. So V0M would be what? Would be AV times Vs, right? AV times Vs. Magnitude, the magnitude of the gain times Vs. Okay, so this is the picture that we have. Now, what is the, are you seeing that what is the collector emitter voltage? Instantaneous value of VCE. What is the collector emitter voltage? Instantaneous value of collector emitter voltage. We said VCEQ is 2 volt. At this point, how much do you think is the VCE? Are you all seeing that at this point, what does this gap denote? This VCE, right? Instantaneous value of VCE. So here VCE is what? Small. Here, how much is VCE? Here is 2. And what about here? here is high. So the value of VCE is going up and down. Now, are you seeing that if I increase the value of Vs, what will happen? This will come even closer. What will happen to VCE? What will happen to VCE? Will become smaller. You push this harder. What will happen to VCE? Will become even smaller. Now, as VCE becomes smaller and smaller, what is happening? Eventually, VCE, what happens when VCE becomes smaller? What happens? The transistor will go into saturation. The transistor will go into saturation. So let me redraw this. What may happen is the following. Let me redraw. This is my 1 volt here, right? It may happen that if you push it hard, it may look like this. You'll see clip, and this value is 0.2. Remember what we said, once it goes into the saturation, the voltage is almost 0.2. The voltage is almost 0.2. It's like clipping. It can't go below this. So if you push your signal hard, Vs, drive even more and more, you will see clipping occurring. Okay. So, and clipping is, which means is distortion. You don't want that distortion. You don't want it in an amplifier. You don't want distortion. You want a nice clean sinusoid. You don't want a distorted sinusoid. So, is this telling you that there's an upper limit of output voltage that I can get? My V0 maximum output voltage that I can get is what? Before clipping occurs. Before clipping occurs, V0 max, to avoid clipping, V0 max has to be less than or equal to what? How high do you think I can drive so that it doesn't get clipped? Three minus 1, 2, 2 minus 0.2, 1.8, right? So which is what? Which is what we are saying is it will be less than VCEQ minus VCE set. Are you all seeing that there is a limit to how large an output voltage I can get? Maximum output voltage that I can get is VCEQ minus VCE set. You can't get more than that. If you try to get more than that, the output will be clipped. The output would get clipped here. That's the maximum that you can get here. Right? So you're seeing the importance of VCEQ. You know, how large an output voltage. Now, of course, how large an output voltage you can get eventually decides how much power you can push into the load. All of that depends on the output voltage. Right? And who decides how large a voltage I can get at the output? VCEQ is deciding that. That's one limit. So VCEQ is not arbitrary. You just put any value of VCEQ. So in that sense, what do you want VCEQ to be? You would like it to be as high as possible, right? To get large output voltage, you want it to be as high as possible. But then, if you want to increase VCEQ, what do you have to compromise? What do you have to compromise? If you would like to increase VCEQ, then what are the options before you? You will have to either decrease the drop here or decrease the drop here, because VCC is fixed, let's say, supply voltage is fixed. So supply voltage is equal to drop here, and drop here. So either you would like to reduce the drop here or would like to reduce the drop here. If you reduce the drop here, what happens? Remember, what is the gain? Gain AV is equal to minus GM RC by VT, and if I write the value of GM is minus IC RC by VT. Who decides the gain of the amplifier? It is this drop. Do you see ICRC? Right? It is ICRC, the drop, which decides the gain.
So
Huh?
There should not be VT in denominator. Minus GMR.
Oh, sorry, minus GMRC, right. VT here, right? Minus GM, minus ICRC by VT. So the drop here, this drop is very important for you. Is deciding the gain. This drop is deciding what? The swing. Now what is this drop deciding? There's a drop here also. This drop is deciding IE. Why can't I make it smaller and smaller? Make this drop smaller. Right now, remember, we put R equal to 1K and this, we put it 1 volt. Why not make it half volt? Very small. This point I'll actually decides the stability, beta stability. Because remember, in the extreme case, what will you do? Make this point, remove RE altogether. If you remove RE altogether, what did we get? Beta instability. So you're going to act as you reduce this voltage from here to here, what you are doing is you're making the circuit more and more sensitive to beta. You're making the circuit more and more sensitive to beta. So are you seeing now what is the role? I mean, in all these engineering designs, you see all these trade-offs. There's not, I mean, you know, you try to touch one thing, something else goes bad. So this is important. So we see the importance of this, we see the importance of this, and this is also important. The drop here is also important. It decides beta instability. How stable is my circuit biasing, how stable is my biasing here. But even before that, there's another thing that you need to see here. And we'll stop after that. So let me redraw the amplifier here. So this is our amplifier here. Same diagram, I'm going to focus on this node here, VCC. So I'm going to draw this here. Right, I'm going to draw this, and this one for us was, this node here was 3 volt, this one was 1 volt. So I'm going to draw this line here. This was my DC value. This was my DC value, which was VC. This was my DC value, which was VE. Right? Okay? And we said, let me draw another value, another line here. Another line is my VCC here. Right? VCC here. VCC. Now remember what we said? We said that my actual voltage at this particular node goes like this, right? The voltage goes like this. The actual value VC is equal to the DC value plus the output value here. Plus the output value here. Okay? Now are you seeing the VC is the DC value plus the output whatever is this maximum value here. We are calling this V0M. How high do you think V0M can be? Earlier we were focusing on the transistor going into saturation and all that, right? We were focusing transistor going into saturation. But let's look at the other side. Don't you see that Vc plus V0M has to be less than? Has to be less than? VCC. How can this voltage rise above VCC? Cannot. Correct? So from here what you are seeing is that the maximum output voltage has to be less than VCC minus VC. You are getting this limit also. You're getting this limit also. VOM cannot be, because this point, the top point, at the most what can happen? It can touch VCC. Can't go beyond VCC. So VOM must be less than VCC minus VCC. Okay? So are you seeing that there are two limits on VOM? One limit was saying what? VOM was VCE minus VC sat, and the other limit is saying VOM is also less than VCC minus VC here. Okay? Keep both these limits in mind. And now tell me about these designs. So here is one design. Somebody designs like this. I'll not give you the values, but somebody designs, say this is 6 volt. Somebody designs this as 1 volt. Somebody designs this as 2 volt. Right? What is the highest V0M that you can get? Maximum output voltage that you can get. Maximum output voltage swing. Maximum output voltage swing would be, it would be decided by what? It would be decided by this factor, VCE minus, it has to be less than this. So VC is, sorry, this is 2 minus 1, 1. It will be only be 0.8 volt, right? So what is this design doing? It created 6 minus 2, it created 4 volt here, right? Drop. It created a 4 volt drop here, 1 volt drop here, and 1 volt drop here. So what is this design doing? It's compromising the swing, but its gain would be how much? 4 volt minus 4 by 26 millivolt. Its gain would be very high. Right? ICRC divided by VT. So its gain would be very high. Another design somebody does, another design that somebody does is like this here. Somebody does a design like this. Say beta stability, that person keeps the same, 1 volt. And then this person does 5 volt here. Is that a good design, do you think? Bias is like this. He sets this is 6 volt, same. He sets this to be 5, sets this to be 1. Is that a good design? No, but you know, somebody sets 5 here and 1 here. What do you think is the maximum voltage swing? Remember the other limit was VCC minus V capital. So what do you think will be the output swing here? 6 minus 5, less than 1, right? Because it's decided by this. And so the person didn't get a higher swing. And the person also lost the gain would be 1 by 26 millivolt. The person also lost the gain also. Nothing is gained. You lost the gain also and you lost the swing also, because swing is not decided by this now. There are two factors. Either is decided by this or is decided by this. Whichever one is minimum. Whichever one is minimum here. So you defeat the purpose of putting it 5 and 1 here. Another person does this. Do you think this is a better design? Another person gives equal importance maybe to both of them. So he sets 6 here, and if this is 1, maybe sets it at 3.5. What do you think about this design? 6, 3.5, 1. Right? This is design number 1, design number 2, design number 3. So this person decides supply voltage is 6, says I will set this as 3.5, this is 1 volt. So this now, what will be the swing decided by? 3.5 minus 1, 2.5 minus 0.2, about 2.2 volt, right? And there's enough voltage drop also, 2.5, to give rise to voltage swing also, to give rise to gain also. So this may look like a better design in the sense that it's trying to achieve the gain also and the swing also. The first design is trying to achieve the gain and compromise on the swing. The second design, it didn't do anything. It didn't get gain and it didn't get swing also. The third design tried to get both. Moderate gain, not gain as high as this, but try to get the swing also, right? So you see this balancing act that takes place here. So many times what people say is, well, if you have 6 volt here, right? If you have supply voltage here, you decide how much voltage you need for bias stability, 1 volt, 2 volt, or whatever it is, right? And if you require 2 volt for bias stability, then you are left with 4 volt. And what you do is, you divide them half and half. Put half here and put half here. You know, that's a strategy that sometimes people use. But of course, it depends on which is more important for you. Are you looking more for voltage swing? Are you looking more for voltage gain? And accordingly, you decide how much is going to appear here, how much is going to appear here, right? So finally, in this, you should be aware of that when I have a circuit like this, I have a drop here, I have 3 drops here. I have 3 drops here, right? I have a drop here, I have a drop here, and I have a drop here. 3 drops here. And it's a part of the design to decide now how much to put here, how much to put here, and how much to put here. Okay? So that is what one will have to decide as to what we do. Okay? So let's stop here. Please submit that one sheet there, and then we